Welcome back to another lesson. Let us conclude the theory part of this section by discussing the mean squared error. The mean squared error is calculated in much the same way as the general loss equation from earlier, except now we will consider the bias value as well, since that is also a parameter that needs to be updated during the training process. The mean squared error is best explained with an illustration. Suppose we had a bunch of values, and we start by drawing some regression line parameterized by a random set of weight and bias values. As before, the errors correspond to how far the actual value is from the predicted value, the vertical distance between them. The error for each point, by comparing the predicted values made by our linear model with the actual values using the following formula, each point is associated with an error, which means we would need to take the summation of the error for each point. Do note that the prediction can be rewritten as Wx plus b. As we are calculating the mean squared error, we then take the average by dividing by the number of data points. And I mentioned before, the gradient of the error function should take us in the direction of the greatest increase in error, so naturally, by moving towards the negative of the gradient of our cost function, we move in the direction of greatest descent, in the direction of the smallest error. We will use this gradient as a compass to always take us downhill. For simplicity, in the last video we ignored the presence of a bias, but the error is defined by two parameters, both m and b. We're not going to go through the math since PyTorch does all of it for us out of the box, but really, it's the exact same concept as earlier, where we differentiate our error function, but this time, since our error function is defined by two parameters m and b, we compute a partial derivative for each, and just like before we start with any m and b value pair, we use the gradient descent algorithm to update m and b in the direction of the least error. And we update them based on the two partial derivatives up above, such that for every single iteration, the new weight is equal to the old weight minus its gradient times the learning rate, and the new bias value is equal to the old bias value minus its corresponding gradient value times the learning rate. When implementing gradient descent into our code, we're not going to have to worry too much about the math, as PyTorch does all of it for us out of the box. It's just nice to know what's going on under the hood when you write your code. The main idea being, we start with some random model with a random set of weight and bias value parameters. This random model will tend to have a large error function, a large cost function, and we then use gradient descent to update the weights of our model in the direction of the least error, minimizing that error to return an optimized model. That is all, guys. Let's put all of this into code. I will see you then.